Part 4, Perceptual Modeling. The reality of the visual percept motivates a perceptual modeling approach in which we describe vision as an input-output function beginning with a two-dimensional visual stimulus and ending with a three-dimensional perceptual object. For example, this figure here stimulates a three-dimensional percept of a box in a corner, so the perceptual transformation is the transformation from this two-dimensional stimulus into this vivid three-dimensional percept. In the case of Peter Tsay's volumetric worm, the perceptual transformation of this two-dimensional stimulus is this three-dimensional object. Now we see a regular spiral cylinder with hemispherical end caps wrapped around a white cylinder, complete with amodal completion behind the occluding cylinder. There's obviously some kind of simplicity metric in effect here, where this is judged as the simplest interpretation of that particular stimulus. And the simplicity metric appears to be based on symmetry, the circular symmetry of the cylindrical cross-section, the spiral symmetry of the central axis, and the circular symmetry of the occluding white column. This is the Gestalt principle of pregnance. The simplest interpretation is the one that the visual system seems to prefer. But that symmetry must be detected in full three dimensions because there is no symmetry in the two-dimensional projection. Likewise with Peter Tsay's sea monster, the perceptual transformation goes from this to this, complete with a percept of the amodal completion of the serpent under the milky surface of the water. Again, there appears to be a simplicity metric in effect here, but the symmetry must be detected in full three dimensions because there is no symmetry in the two-dimensional projection. This leads to somewhat of a chicken and egg problem because the perceptual image must be reified before you can even detect its symmetry, but the symmetry is required in order to reify the perceptual image. This is indeed a manifestation of the inverse optics problem. All of these quadrilaterals project to the same retinal image because the optical projection of the eye collapses them all of these three-dimensional shapes into a two-dimensional projection in the normal optical projection. The idea of the inverse optics problem is to attempt to invert the projection, and from this one rectangle, we'd like to reconstruct all of the possible rectangles that could possibly have projected to it. Now, this is a mathematically under-constrained problem because there are an infinite range of quadrilaterals that all match to this surface. So this is practically impossible to compute using normal sequential algorithms. How on earth does the visual system resolve the inverse optics problem? Part 5, Gestalt theory.